Welcome to this new video. So previous lecture we discussed about various strengthening mechanisms. So today we will discuss about a heat treatment process known as annealing. So there are many different kinds of heat treatment for materials. So annealing is a process of heating a material to a particular temperature and then cooling it very slowly. So the metal is heated to a temperature above its recrystallization temperature and kept at that temperature for a particular period of time, and it will be followed by a very small cooling in order to develop a equilibrium structure in the material. So the cooling is done in the furnace itself. Okay, so here annealing is a heat treatment that alters the physical and sometimes chemical properties of a material to increase its ductility and reduce its hardness and making it more workable. So here the ductility is increased and the hardness is decreased in the material, and the material will get more workable, so that the workability of the material will be increased by increasing the ductility and in turn reducing the hardness of the material. So the amount of process initiating Gibbs free energy in a deformed metal is also reduced by the annealing process. So the amount of process initiating the Gibbs free energy will be reduced due to this annealing process. So this Gibbs energy in practice and industry, and this reduction of Gibbs energy is termed as a stress relief. So annealing is basically a three-stage process. So these three stages of annealing process that proceed as the temperature of the material increased. As the temperature increases, the stages will be changed one by one. So these stages are recovery, recrystallization, and grain growth. So recovery, recrystallization, and grain growth, these are the properties and structures changed during cold working. The properties and structures changed during cold working may revert back to the pre-cold work states by appropriate heat treatment, and such restoration results from two different processes that occur at elevated temperatures, that is recovery and recrystallization, which may be followed by grain growth. That is, when a deformed material, when it is heated, the properties get restored to its earliest stage. So the results are formed from two different processes, that is recovery and recrystallization, and followed by another third stage known as grain growth. So these are the three stages. So now let us look one by one. So the first stage is recovery. So now let us look what is happening. So in recovery is a process by which the deformed grain size reduce their stored energy by the removal or rearrangement of defects in their crystal structure. So the deformed grains reduces the stored energy by removing or rearranging the defects in their crystal structure. So the stored energy will be reduced. So these defects, primarily dislocations, they are introduced by a plastic deformation of the material and act to increase the yield strength of a material. So since the recovery reduces the dislocation density, the process is normally accompanied by a reduction in material strength and a simultaneous increase in the ductility. So as a result, the strength of the material will be reduced and the ductility will be increased due to the decrease in the dislocation density. So when the dislocation density is reduced, it will be followed by the reduction in material strength and the increase in the ductility of the material. So in addition, physical properties such as electrical and thermal conductivities are recovered to their pre-cold work states. So the process results in the restoration of the physical properties. So in recovery, there will be a relief of some of the internal strain energy of a previously cold work material. So that is the recovery stage. So next is the next stage is a recrystallization stage. So in recrystallization stage, there will be formation of a new set of strain-free grains and within the previously cold work material. So even after the recovery is complete, the grains are still in a relatively high energy state. And the recrystallization is the formation of a new set of strain-free and equiaxed grains that is having approximately equal dimensions in all directions and that have low dislocation densities and are characteristics of a pre-cold work condition. Okay, so the driving force to produce this new grain structure is the difference in internal energy between the strained and unstrained material. So the new grains form as very small nuclei and grow until they completely replace the parent material. So a new set of strain-free grains will be formed and the grain refinement occurs. So during recrystallization, the mechanical properties that were changed as a result of cold working are restored to their pre-cold worked values. That is, the metal becomes softer, weaker, yet more ductile. So during this process, the material restores its pre-cold worked values and making the material ductile but softer and weaker. So the recrystallization behavior of a particular metal alloy is sometimes specified in terms of a recrystallization temperature and the temperature at which the recrystallization just reaches the completion. So the behavior of the materials are specified by its recrystallization temperature. So next, typically it is between 1/3 and 1/2 of the absolute melting temperature of a metal or alloy and depends on several factors including amount of prior cold work and the purity of the alloy. So this recrystallization temperature is between 1/3 and 1/2 of the absolute melting temperature of the metal or the alloy and it depends on the factors including the amount of prior cold work and the purity of the alloy. So recrystallization temperature proceeds more rapidly in pure metals than in alloys. Thus alloying raises the recrystallization temperature. So recrystallization temperature, you can see it is higher in alloys than in pure metals. So recrystallization temperature is normally 0.3 Tm, where Tm is the absolute melting temperature. For some commercial alloys it may turn as high as 0.7 Tm. So for normal materials, the melting point, the recrystallization temperature will be 0.3 times the melting temperature of the material. So these are some examples of the recrystallization and melting temperature for various metals and alloys. So here we can see for lead, the recrystallization temperature will be -4 degrees Celsius, whereas the melting temperature is 327 degrees Celsius. And for tin also, the recrystallization temperature is -4 and the melting temperature is 232. So here we can see tungsten is having a high recrystallization temperature of 1200 degrees Celsius and also a melting temperature is around 3410 degrees Celsius. So these are the different melting temperatures for zinc, aluminum, copper, brass, nickel, iron, etc. So next we can see the difference between hot working and cold working. So cold working, we know that is a mechanical deformation of a metal at a relatively low temperature, whereas whereas in hot working the temperature is above the recrystallization temperature. So the difference is hot working takes place at a temperature above the recrystallization temperature, and cold working will be below the recrystallization temperature. So in hot working, new crystals will be formed, whereas there will be no crystal formation in cold working. So the surface finish of the hot working is not good. That is not a very smooth surface finish, but the surface finish is good in the case of cold working. So, and there will be no residual stress in hot working, and there will be some residual stress formation in cold working. And we know that in hot working we require only a very less force, but as it is a cold working we require a more force, and more force will be required in cold working. So these are the difference between hot working and cold working. So here we can see a relation between annealing temperature with ductility and the tensile strength. So as these are the three different stages: recovery, recrystallization and grain growth. And we can see as the annealing temperature increases, the tensile strength will be reduced, and this is the percentage of reduction in tensile strength. So the tensile strength will get reduced, but the ductility of the material increases with the increase in the annealing temperature. So the ductility gets increased and the tensile strength will be reduced. So here also we can see the change in grain size. So the grain size after a particular recrystallization stage, after a partial recrystallization, so the grain size will also start increasing, and in the third stage the grain size will be much larger than the previous stages, and the new grains also will be formed in the recrystallization stage, and that new grains also will, the size of that new grains also will be increased. So this is the relation between the annealing temperature with respect to the tensile strength and ductility and the grain size. So next stage or the third stage is grain growth. So after the recrystallization is complete, the strain-free grains will continue to grow if the metal specimen is left at an elevated temperature. The phenomenon is called grain growth. So if we keep on increasing the temperature, the strain-free grains or the grain size will be increasing with the increase in the temperature. So as the grain size increase, the total boundary area decreases and yielding at an attendant reduction in the total energy. So the total energy will be yielding, and this driving force for grain growth, and the yielding in the reduction in the total energy will be the driving force for the grain growth. So grain growth occurs by the migration of grain boundaries. So the grain boundaries get migrated and the grain size will be increased. So not all grains can enlarge, but large ones grow at expense of small ones that shrink. So here all the grains will not be enlarged, but some ones grow with the overcoming the overlap, or we can say overlapping the small grains. So small grains get shrinked and the large grains, some grains will continue to grow. So thus the average grain size increases with time, and at any particular instant there will exist a range of grain sizes. So the grain size will increase with time, and there will be a range of grain sizes. So here we can see a grain growth with respect to with the temperature. So in the first figure you can see at a 580 degrees Celsius, after 50 minutes the grain size will look like this. so there will be a lot of grains and lot of grain boundaries will be there. So but in this microstructure we can see the grain growth after 10 minutes when it is when the temperature is at 700 degrees Celsius. So at 700 degrees Celsius after 10 minutes we can see a rapid change in the grain size, and it will look like somewhat like this. Okay, that's how the grain growth is taking place with respect to temperature. So the temperature increases, the grain growth will or the grain size will also keep on increasing. So grain growth is the increase in the average grain size of a polycrystalline material or the material. So the grain diameter D varies with the time T according to the relationship. And the relationship is d raised to n minus d0 raised to n is equal to k into t. So here d0 is the initial grain diameter at a time we can say 0. At a time that equal to 0 seconds we can say the d0 is the initial grain diameter, and k and n are time independent constants. This k and n are time independent constants, and this n will generally be greater than or equal to 2. Okay, so the mechanical properties at room temperature of a fine grained material are usually superior to those of coarse grained ones. So the properties of fine grained materials will always be superior, that is it will have a high strength and toughness to those of a coarse grained ones. So if the grain structure of a single phase alloy is coarser than that desired, refinement may be accomplished by plastically deforming the material and then subjecting it to a recrystallization heat treatment. So here we can see the changes in properties with the percentage of cold work and the annealing. So with the increase in temperature, the annealing temperature leads to recovery and recrystallization and maybe to grain growth, as I said. So there are 3 stages. So during the process of annealing, the strength and hardness will be decreased over the process, and it will result in the increase of ductility and also the formability. So first is the deformed state. As you can see here, it have high density and high internal stresses, and when the increase in the annealing temperature, the first stage is recovery stage, and in recovery stage the partial defect annihilation and rearrangement will be taking place. And next is the recrystallization stage, and the first is the partially recrystallized stage. We can see the grains, new grains, strain free grains are generated, and moving the grain boundaries and also the sweeping the structure will take place over the partial recrystallization stage. And when after the full completion of the recrystallization stage, the grains get fully recrystallized and the deformation substructure will be removed. And the final stage is the grain growth, and it will be the competitive coarsening of the grains, and the grain size will increase, and also the grain boundaries also will be increased. So that's all about the annealing process, the 3 different stages, and how the process of annealing is taking place, and the strength and hardness that will getting reduced, and thereby increasing the ductility and formability of the material. So with this we come to the end of second module. So in the next video we will start the third module. Thank you for listening.